Hello students. Our next topic is bubble chamber and semiconductor detector. First we go through bubble chamber. It is a high energetic particle detector discovered by D.A. Glaser at the University of Michigan in 1952. It is a high energy particle detector. Principle. We know that normally the liquid boils with the evolution of bubbles of vapors at the boiling point. If the liquid is heated under high pressure, its boiling point is raised above the normal boiling point without boiling taking place. Okay? If we heat the liquid under high pressure, its boiling point is raised above the level without boiling. Okay. And a sudden release of pressure will leave the liquid in a superheated state, and the liquid does not boil immediately but remains quiet for some time. If an ionizing particle is incident on the liquid just after the release of pressure, the ions left in the track of the particle act as the condensation centers for the formation of bubbles. This is the principle on which bubble chamber works. Okay. This is the construction detail. It consists of a cylindrical chamber containing liquid. This is a cylindrical chamber containing liquid. A piston is arranged here. To superheat the liquid, a mechanism with bellows and expansion piston is fitted with the cylinder. So you can see the bellows and expansion piston arranged here to impose high pressure on the liquid. The top and bottom of the cylinders are provided with optically plain glass plate. These are the optically plain glass plates which covers the top and bottom of the cylinder. The whole system is enclosed in a temperature control. This is the whole system enclosed in a temperature control. Light from a flashlight enters the cylinder. This is the light flash tube, and here you can see a camera, and also coils for magnetic field are also provided on two sides of the enclosure. So a camera is fitted at the top of the cylinder to take the photograph of the cylinder. The bubble chamber is used in conjunction with electromagnets to determine the sign of the charge and momentum of the particles. Now, what is the work? The operation cycle of the bubble chamber consists of 4 stages. First, the liquid is first heated to a temperature above its boiling point. It is kept in the liquid state by the application of pressure greater than its saturation vapor pressure. Okay. It is kept at a higher pressure. The pressure is suddenly released so that the liquid becomes superheated, and the flash lamp is switched on just before the pressure falls to minimum. Okay, from this you get the radiation, and hence there is a condensation of uh, bubbles occurs during the stage of suddenly the release of pressure. So by suddenly releasing the pressure, the liquid gets superheated, and when at the same time the flash lamp is switched on to get that condensation. Now the growth of the bubbles occur for about milliseconds, and the centers of the bubble formation last for about the same time. A powerful lamp is then switched on within a millisecond to photograph the track. This cycle is then repeated. This is how we detect using this bubble chamber. Next is semiconductor detectors. These are essentially reverse bias junction types. They have several advantages over other type of radiation detectors. They have better energy resolution, linear response over a wide range of energies of the incident radiation, and fast time response. So a semiconductor detector consists of a semiconductor crystal sandwiched between two conducting electrodes. So are the two conducting electrodes. This is the crystal which is sandwiched between the two conducting electrodes. An electric field is applied across the electrode. Passage of nuclear radiation produces whole electron pair, which should move towards the appropriate electrode, and the charge collected is used as a signal for the detection of radiation. So when ionizing radiation passes through the crystal, it produces electron hole pair, and it moves towards this is the negative terminal, this is the positive terminal, it goes towards the corresponding terminals, and the charge collected is used as a signal for the detection of radiation. Okay, this is the principle of semiconductor detector. There are two types of semiconductor detectors. First one is diffusion junction detectors, and the second is surface barrier detector. First we go on to diffusion junction detector. In a PN junction diode, the electrons from the N region and the holes from the P region diffuse into the P and N regions respectively across the junction, and it forms a double layer of charges which prevent from further diffusion, and a self-adjusted potential barrier is created at the junction. Now, if now the P region is connected to the negative terminal of the battery and the N region to the positive terminal, the arrangement is said to be reverse biased. You can see the figure in the next slide. As a result, electrons and holes are drawn away from the junction region, and the depletion layer is formed at the junction in which no charge carriers are present. Okay. So due to reverse bias, no current flow through the junction and the diode is cut off. The thickness of the depletion region depends on the nature of the impurities on the and on the voltage applied. It usually lies in the range of several hundred microns to few millimeters. Since the conductivity of the depletion layer is low, a large potential difference can be maintained across it. So it acts like an ionization chamber. So this acts like an ionization chamber. So this is the ionizing radiation entering the depletion region. These are the P and N regions across which we have connected a variable voltage source and a detector and an amplifier. This is the arrangement. Now, if a high energy charged particle passes through the depletion layer, electron hole pairs are generated inside that. The electrons are raised to the conduction band and are free to move through the crystal under the action of applied electric field. The holes left behind the valence bond are also moving freely through the crystal. Due to both of these reasons, a momentary current pulse proportional to the number of electrons and holes are produced. So, these produced electrons and hole pairs moves to the corresponding electrons and produces a momentary current impulse. Okay. Thus, the semiconductor detectors acts like a solid state ionization chamber. Okay, we detect this current impulse proportional to the number of electrons and holes produced. Since the energy needed to produce an electron hole pair is only about 3 electron volt, compared to about 30 electron volt required to produce an electron hole pair in a gas ionization chamber, the registration of the electrical pulses in semiconductor detector is easier, and the accuracy of energy measurement is much better. In fact, semiconductor detectors have the best energy resolution amongst all type of radiation detectors for most purposes. This is the most reliable source of detection, semiconductor detectors. Because of the narrow width of the depletion region, the pulse rise time is very small. This is the only drawback of this. It is only about 10 to minus 8 seconds for these detectors.